All right, so I see some of the proposals coming in to my email. Thanks. Keep them coming. Send me an email, please. And I will evaluate and get back to you by Wednesday. Okay, start looking at them soon. All right. Last lecture we were talking about, we're basically having a sort of introduction to the whole real idea of a photon and the heart of quantum optics about understanding the distinctions between what we call classical light and non-classical light. It's more than just a stamp collecting exercise of putting it into two different boxes. The question of classical versus non-classical light is an important question for the issue of how we access the resources of non-classicality for fun and profit. One of the ways, of course, that we think about photons is by counting them. And physically, the way we typically do that is thinking about the photoelectric effect as a mechanism of counting photons. So when photons come into the material that ejects photoelectrons, we count ultimately those electrons, right? But those electrons are ejected through the fact that the material is being impinged upon by photons, or so we think. Because, in fact, as we discussed last lecture, we can model the interaction that happens at the detector in this measurement process in a semi-classical model. And by semi-classical, we mean we treat the matter quantumly, but the field classically as a classical electromagnetic field. And in which case we can think about the process by which we eject a photoelectron as a kind of ionization process, and just use Fermi's golden rule to calculate the rate at which those photoelectrons would be ejected from the material. Okay? And Fermi's golden rule tells us then that this rate is just going to be proportional to the local intensity at the material. Okay? So if we have some kind of photon counter here, which we impinge some light beam on it, if this is set up to be a kind of Geiger counter, we'll see some clicks in the current, photocurrent as a function of time, representing photon counts. And the degree to which this ionization process is a random process, uncorrelated from instant to instant, would say that this process we expect to be a Poisson process. The randomness here is being explained or arises from the random photoionization events. Okay. Now, of course, there's a lot, there's a lot of subtlety here. I mean, when did the randomness happen? I mean, we have the Schroeder equation. So in the end, it's, the measurement, when the measurement occurs and something random, God knows. I mean, I'll ask God when I get there, if I get there, I don't know. So one question, please explain the measurement problem to me, and then I can lose existence on the fine. But that's what we see, right? And this model of a photon detection had nothing to do with an A or an A dagger. There were no photons to be found. This h bar omega that appears in Fermi's golden rule comes from the Schrodinger equation with a time dependent. There's no quantization of the field that was required to get this. Okay. Now, as we described, one of the essential aspects of what we call a photon is that a photon is a particle. And what we mean by a particle is that it's indivisible. We can't divide a photon in half, which means we can't detect a half of a photon. So if we were to send a single photon onto a beam splitter and we put two detectors, one on the reflected port and one on the transmitted port, only one of these detectors should ever go click, never both. In the instant in which that photon, we only have one photon in that window. And so this was an experiment that was done, the first experiment to kind of prepare single photons was done out of the Aspect group in Paris. Philippe Rongier was his student at the time. He's now a very famous quantum mathematician in his own right. And I think it was his PhD thesis where they did this work, where they prepared single photons in this correlated photon experiment, which we'll talk more about next semester. But the bottom line of this was they looked at the coincidence counts here, and as long as not two photons were impinging on this beam splitter in the time window, what they would see is the probability of coincidence was less than the probability of transmission time for reflection. In fact, it was close to zero for those cases where we can avoid these kinds of two photons impinging in the time window. Okay. Now, importantly, if I took a laser beam and I put in an attenuator that made it so that this rate of photons, the rate is just proportional to the power that is impinging. If I turn down that power enough by attenuating this beam very strongly, then on average, I might have in whatever window I'm using to do this detection window over here, this integration time, I could have it that the average number of photons in that time interval is much, 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 much less than 1. I can do that. I can just basically put up something that almost blocks almost all the light at it. So you might think that's a way of making a single photon source. Because, yeah, most of the time there's nothing. But every once in a while, there's a photon. And then you look for that, and that would seem to be a pretty natural way of doing that. But in fact, that's not what happens at all. We'll get into this in some detail through the remainder of the semester. And in fact, in this case, it's equal for the laser. In fact, classically, this coincidence count always has to be greater than or equal to. It can be greater than if I have extra fluctuations in the problem, intensity fluctuations. But if I have a definite intensity in this thing, I'm going to have whatever fraction of the intensity goes here or here, and the product of them is what the total was. So the case of a laser is not in any way the case of the single photon. You can't make a single photon by just attenuating. In fact, the laser is as close as we can get to a classical optical field in nature. It looks like the classical wave, which a certain fraction goes here and a certain fraction goes here always. And so we want to understand that. And that's our goal starting today. All right. So we want to talk about what we call quasi-classical light. Now, why quasi? Well, there's still quantum mechanics, and we have to still obey the rules of quantum theory. But we want this to be something which looks as close as possible to the classical theory. I'll just call it the classical waves, with minimal quantum uncertainty. Consistent with the Heisenberg principle. So that's what we want to look for. How do we describe, within the context of quantum field theory, states of the quantum electromagnetic field that look as close as possible to the classical theory with the minimal fluctuations? Okay? So we seek states of the quantized field which satisfy this. All right? So let's, for simplicity, let's just think about a single mode of the quantized field. Okay, so it doesn't matter whether I'm talking about a mode in a cavity or a traveling wave mode. Let's just, for simplicity here, let's just think about plane waves. It doesn't really matter what mode I'm looking at. Okay, so for this single mode, my quantized electromagnetic field at some position and time is got some amplitude. We have just not even going to denote that because it's just that one mode. Okay, so this is the annihilation operator for that mode. Since there's only one, I'm not going to put stick a label on it. Okay? Now, let's remind ourselves how we quantize the field in the first place. When we quantize the field, a kind of simple-minded way of doing that was to think about a simple harmonic oscillator which had, you know, quadratures. Or a complex amplitude, right? And the way we quantized it is how? Well, we just put a hat on it, right? So we said, let's put a hat on it. So to quantize, we took the complex amplitudes and we turned them into these operators A, which we later realized corresponded to the annihilation operators that annihilated photons from the field, or lowered the Fock state ladder, right? So, anyone have a suggestion of how I unquantize? Want to take the hat off. So, to unquantize, I want to somehow look for a state of the field for which I can replace the A's by alphas. All right? So, it's not clear I can do that, but one way I can do that is I'm going to seek a state of the field for this mode such that it is an eigenstate of the annihilation operator. Now, it's not necessarily the case that such states exist, because this is not a Hermitian operator. In fact, it's not even what we call a normal operator. A normal operator is an operator that commutes with its adjoint. And this doesn't commute with this adjoint. And only for operators that commute with their adjoints are we guaranteed that there exists eigenvectors of those operators. In fact, there is no eigenvector of a dagger. There are these states which are eigenvectors of A. Turns out, just as chance would have it. These are called the quasi-classical states, and for historic reasons that we still stick with today, these are called the coherent states, because they're related to optical coherence theory, and we're going to talk about that. Yeah, Matt?
What's the broad of the eigenvector of A?
It's true. There is, this statement is also true. Absolutely, I can take that. But there's no right eigenvector of A dagger. So this is a left eigenvector, and this is the right. That's what I mean by that. Now we'll come back to show by construction a number of ways that we can prove that these states exist and what they are, but let's just think a little bit about their property. Okay. Why these? Well, this is going to give us the kind of unquantization, but getting the classical properties that we want. What we want to see were the states that were as close as possible to the classical waves. They should have, so what we want to have be true is that the mean field should follow classical evolution. E.g. free field. So we can think about the case of the free field, for example. Now, you might have guessed, well, the eigenstates of the Hamiltonian might be a good guess for what the states were should do that. I might have considered a Fock state. But what is the expected value of the electric field operator in this case? It's 0, right? This is 0 because this is 0. So this is not going to follow something that looks like what we'd expect if I were to look at, say, the electric field, forget about the vector nature, as a function of time. What I should see is the mean field I expect as a function of time at some fixed position should look like this. And this doesn't do that. But this coherent state does. So let's calculate that. So firstly, I'm going to forget about the vector nature. And I'm just going to say, or I'll just take it to be linearly polarized and just take the vector out. I'm going to rewrite this. It's got this amplitude. And it's got a x cosine omega t minus k dot r plus p sine omega t minus k dot r. Or equivalently, this is the real part, or the Hermitian part, I have that stupid root 2 here behind that. Where we should just go. Did it fall down there? Oh yeah, that's a fair point. That's a bad design. Thank you. So, now I ask you, what is the mean field of this in the case of the coherent state? Well, I can, this is proportional to right? And what is this? Well, this is an eigenstate. So the mean field of alpha for the case of the Fock state, for A was 0, but for the coherent state is alpha. And what about this one? Alpha star, for exactly the reason that Matt was suggesting. Or I could just take the complex conjugate of this, because that's what this is. Right? And because this stupid board doesn't go up and I can't remember that, I have to be careful about that. This mean field is proportional to the real part of alpha e to the I minus omega t which is the classical field. Let's come back to this board. So, the mean electric field follows exactly the classical evolution of just that mode oscillating as a simple harmonic oscillator with two quadratures, or an amplitude and a phase. What is the mean quadrature x for a coherent state? Well, this is equal to a plus a dagger over root 2, right? Which is equal to alpha plus alpha star over root 2. This is equal to root 2 times the real part of alpha. What about the mean quadrature p? Well, that's a minus a dagger over I root 2, which is alpha minus alpha star over I root 2, which is root 2 over the imaginary times the imaginary part of alpha. So the eigenvalue alpha represents the classical complex amplitude of an equivalent mode of the harmonic oscillator with two quadratures, x and p. The real part of this, with a certain e to the I, has a cosine part and a sine part. Okay, so what about the other aspect of this? The question that not only should the mean of the electric field operator evolve in time exactly as the classical wave evolves, but we also want this to have minimum quantum fluctuations. I mean, if I were to measure the electric field, I wouldn't get a definite answer, because I can't have this be simultaneously an eigenstate of x and p. If it was simultaneously an eigenstate of x and p, well, then I would have both quadratures at any time, and it would be some definite thing. Okay? But this is the best compromise. This is the best compromise because it's not an eigenstate of x and p, but it's an eigenstate of the combination of x and p. Nonetheless, it's not an eigenstate of x, nor is it an eigenstate of p. We know what those are. Those are the position and momentum eigenstates. And that's not what this is. This is an eigenstate of A. So there will be quantum fluctuations on this, which is to say, if I measure it, I'm not going to get a definite answer. So, I ask you then, what are the quantum fluctuations in x and p? How do I calculate them? Right, I look at just the variance, I look at the fluctuation. So what we're interested in is what are the fluctuations in x, right? That's the square root of the mean of x squared minus mean of x squared, right? So let's calculate that. What is this? Well, we know how this is an eigenstate of A on the right, and this is an eigenstate of A dagger on the left. So let's plug in what we have. This is equal to A plus A dagger over root 2 squared, or 1/2 A squared plus A dagger squared plus A dagger plus A dagger A. Right? Yes, sir.
So, we haven't shown that we have this coherent state.
That it exists even?
Yeah.
Yeah, we have it. We'll come back to that in
a second. I wanted to see what if this existed, what would its properties be?
Yeah. So, how are you going to calculate this?
Commutator.
Exactly. So, what we know, again, to emphasize what we had over here, we know how a dagger acts to the left on the coherent state, and we know how A acts on the right. So we got to put all the A's on the right and all the A daggers on the left whenever we take expectation values with respect to coherent states. And doing so means commuting this into normal order. Normal order, as we will talk about in much more detail next semester, means all the A's to the left and the A daggers, I'm sorry, I'm dyslexic. A's, no. Yeah, A's to the right and A daggers to the left. Okay. So, that means this is not in normal order, but we can commute it into normal order. So that means we replace this with this plus the commutator, which is 1. So this is equal to a half times, well, every now A acts to the right gives me an alpha, every A dagger acting to the left gives me an alpha star. So this is equal to alpha plus alpha star squared plus a half. Right? Because I'm going to get alpha squared plus alpha star squared plus twice alpha alpha star plus 1. That's that. Okay. So, with that said, what we have then is that delta x squared, well, we have x squared over here. That's this guy. So this minus that is a half, coming from the commutator. The commutator, the fact that A and A dagger don't commute, is a reflection of the uncertainty principle and the quantum fluctuations that exist in this quadrature for this term, or equivalently, delta x is 1 over root 2. And similarly, you can go through exactly the same calculation and find that this is true. And, of course, then delta x times delta p is equal to a half. And this is minimal. So this is nice. I mean, we can have other distributions of x and p, which multiply to this, but this is, in some sense, equally distributed. It doesn't pick one quadrature over, and that seems would be a natural thing to think about if we wanted to have a state that was just quasi-classical with just random quantum fluctuations on top of it. Like that. In fact, we can think about this in a kind of phase space picture. So classically, we had a phase space with these funny factors of root 2, right? And we said, you know, the things that were energy eigenstates were sort of like being on an energy shell in a harmonic oscillator, which has a definite radius, but we don't know where it is in x and p. Those are like the Fock states. But if I wanted to think about a coherent state, classically, we have a complex amplitude, and that complex amplitude then rotates around like a free harmonic oscillator. The quantum case in this situation would represent something we cannot specify simultaneously, this to be an eigenstate of x and an eigenstate of p, but we can find a state which has kind of minimal fluctuations. So this was the Fock state in x and p. This thing is centered as a wave packet, which is centered in phase space with a mean x and a mean p. But it also has fluctuations in x and fluctuations in p. And this state is what we call the coherent state. All right. Now, this state, these states, the Fock states, was an eigenstate of the number operator. What about the coherent state? Is it an eigenstate of the number operator? No. This is not an eigenstate of, even if eigenstates existed, it couldn't be simultaneously an eigenstate of any dagger, they don't commute. So this is something, we don't quite know what it is yet unless we do. So this is not surprising, this state is not an energy eigenstate of the harmonic oscillator, free field harmonic oscillator. So, but we can ask the following question: what are the mean number of photons in the mode given a state as a coherent state? What's the answer to that? Alpha times alpha star, or alpha squared. Not surprising, right? The amplitude squared is what we said was the energy classically. And that's that's classical. But this is not an eigenstate of energy. It has uncertainty in the energy, or the number. The energy and the number are just related by h bar omega. So now I ask you, what are the fluctuations in the number? Well, the way we calculate that is we need to look at the mean n squared minus the mean of n squared, which is and how are we going to do that? We normally order it through commutators. So I replace this by a dagger a plus 1. So I have a dagger a plus 1, which is alpha to the 4th plus 1. No, I have this guy, excuse me. The one here gives me a dagger a, so this is plus alpha squared. So from that, we find that the fluctuation in number is what?
Alpha squared.
Alpha squared, which is equal to the mean number. What kind of distribution is one where the fluctuations in number are equal to the mean number? A Poisson distribution. So this is consistent with Poisson. Amazing. It's a random correlation. It just falls right out. Let's prove this now, and then and through that prove that such a states exist, that these coherent states exist. So to do that, let's say, let us write the coherent state as some arbitrary state in Hilbert space. Any arbitrary state in the Hilbert space of the single mode can always be expressed in the basis of Fock states. So we want to show that there exists some set of coefficients C sub n which make this an eigenvector of the annihilation operator. Okay? So let's just apply the annihilation operator to this, and I get so what is this when it acts on that? Square root of n times n minus 1, right? And I only have to start counting from 1 because the ones at 0 are annihilated, okay? And so I can rewrite this now just as a dummy index, ramping it up by 1. Right, starting at 0. Okay? And what is this supposed to equal? This is supposed to equal alpha times that, which is right? So, with that said, I have a recursion relation that says for this equation to be true, I set Cn plus 1 equal to alpha over root n plus 1 Cn. Okay? And so, that tells me that C1 is equal to alpha times C0. C2 is equal to alpha squared over root 2 C0. And C sub n is alpha to the n over square root of n factorial C0. Just doing that recursion. Right? And thus, we have that equation. It's perfectly, thus such exists. Finally, we set C0 through normalization, and then the overall phase by just convention. So the norm of this vector is C0 squared times the sum over n of that. And and that's supposed to equal 1, right? What is this sum? That's an exponential, right? And so this tells me that C0 is equal to some phase, which we take to be 1, e to the minus alpha squared over 2. And so the coherent state can be expressed as a superposition of Fock states in the following way. Alpha to the n over the square root of n factorial e to the minus alpha squared over 2. So, with that, what is the probability of finding n photons in the mode given a coherent state? Well, that's given by the Born rule. Which are the squares of the probability amplitudes, which is equal to alpha squared to the power n over n factorial e to the minus alpha squared, taking this and multiplying it by its complex conjugate, which is equal to alpha squared was the mean number of photons in the mode to the power n over n factorial e to the minus average n, which is a Poisson distribution. Yay! Amazing. So in a coherent state, if we ask at any instant how many photons there are in that mode, it'll be random. The mean number of photons is just the square of the amplitude, which is related to the power or the energy, but there will be fluctuations in the number of photons, and those fluctuations are, as expected, Poissonian. Very good. All right. Now, there's a lot of important algebra associated with dealing with these kinds of coherent states, and some of which we'll deal with in more detail next semester, but there's a few things we want to talk about here. So, if the vacuum is a coherent state, right? If I look at the annihilation operating on that, it's an eigenstate of the annihilation operator with eigenvalue 0. In fact, we can think about the coherent state, the vacuum state, if I think about this in phase space, as having a mean field of 0, but there are quantum fluctuations in x and p. In fact, we know what exactly, not only what the fluctuations in terms of the variance is, as we just calculated, but I can ask, what is the probability of seeing a quadrature x given the vacuum? what do I mean by this? Well, this is, look at this is an eigenvector of the quadrature operator, also known in the harmonic oscillator as the position operator. These are the position eigenvectors, right? This is the wave function of the ground state of the harmonic oscillator in position representation. What is the ground state of the harmonic oscillator? It's a Gaussian, so this is psi 0 of x, right? So this is a Gaussian, and we all know that the way I write a Gaussian is I memorize the formula for a Gaussian. And for the ground state, what is this? What is the mean x? 0. And what's the fluctuations in x? It's over 1 over 2, right? The variance is 1 over 2. So this is equal to e to the minus x squared over square root of pi. Right? That's the probability density of finding that quadrature. Similarly, this is probability. Excuse me. The probability of finding a certain p quadrature is that's the momentum space wave function of the ground state of harmonic oscillator. What the heck is that? Yeah, it's a Gaussian, and what is the form of it? It's exactly the same, right? It's one of the things about harmonic oscillator is that the wave functions look the same in position momentum space. So we have Gaussian fluctuations. These are called Gaussian states. The coherent state is an example of a Gaussian state because the probability distribution in x or p is Gaussian. Actually, in some bizarre way, as we know, the joint probability distribution is also Gaussian, but then more on that later. So, the coherent states that have a different alpha, some other alpha, we say are similar. They have a mean x and a mean p, but the fluctuations in the coherent state are exactly the same, although I didn't draw it anyway like exactly the same. But I meant to. As the vacuum. It's like taking the vacuum fluctuations and displacing it away from the origin. And so we should be able to understand or get at this coherent state mathematically through some kind of unitary transformation in phase space. Okay? So just to be clear about this, I should say that if I were to look at the coherent state for an arbitrary alpha, this would equal so it's just a Gaussian displaced to a different point in phase space. Yes, sir?
So when we write e power minus x squared as is the wave function of the ground state, that x is the quadrature x?
That's correct.
Does it have any connection with the real x's?
So we have not yet talked about how I would measure that. That kind of measurement is known as a homodyne measurement, which we'll talk about next semester. Photon counting is a way of getting the statistics of the number operator, but not the statistics of the quadrature operator. We need to do a different kind of measurement. But if we did such a measurement, what we would find is a random outcome with Gaussian noise, which was sort of loosely depicted here. Excellent question. All right, so I claim that we can get a coherent state by applying a phase space displacement unitary operator. Now there's a lot of ways to think about that. I ask you the following question. If I wanted to displace a state in position, what unitary operator would I apply to the state that takes the state and displaces it in position? What is the generator of position displacements? The momentum operator, right? So e to the minus I xp over h bar displaces in position. And if I write this in dimensionless notation, it's that. Getting rid of the characteristic units. What about a displacement in momentum? What is the generator of displacements in momentum? Position with the minus sign. So e to the plus I p x hat displaces by an amount p. So if I want to both displace in position and momentum, and I want to do so in a way that doesn't bias me to one or the other because x and p don't commute, what should I write as a thing that simultaneously displaces me in position and momentum? Yeah, I want to have both of these guys in the exponent. Now, let's re-express that. If I plug in that x is alpha plus alpha star over root 2, p is alpha minus alpha star over I root 2, x is a plus a dagger hat, and p is a minus a dagger over root 2. I plug in that into here. With a little bit of algebra, you will find that this is equal to alpha a dagger minus alpha star a, which we call typically d of alpha. This is the phase space displacement operator. Memorize this. Okay, so I claim that the coherent state is what you get when you apply the phase space displacement operator to the vacuum. how can we prove that? Any thoughts? There's lots of different ways to do it. One way to do it is to show that when this acts on this, I get this thing. Right? That's one way of doing it. How would I how am I going to take this and apply that to that?
Right out the series.
I could write out the series, but that's going to be a horrible mess because I'm going to have to commute tons of things. So I want to be a little, you're right, that is a definite first approach on your homework. Try it, write out the power series, try to commute all those things. Good luck. Another way is think about how we can express this operator in normal order. Right? Because we know when it's in normal, if I can write this in normal order, then I know how these guys act to that. So, I use Baker-Campbell-Hausdorff. Recall that if I have the exponential of a sum of operators, I can write that as this with a term that relates to the commutator and just truncate it if the commutator itself is something that commutes with A and B. If this is true, then I don't have to have multiple commutators. It just stops there. So in this case, this is A, and this, with the minus sign, is B, right? The commutator of A and B is a number. So it commutes with A and B, so this is good. And what is the commutator of A with B? Well, it's equal to minus alpha squared, the commutator of A, which is minus 1 is alpha squared. Right? So, what that tells me is that this is equal to, putting this in here, e to the minus 1/2 alpha squared, e to the alpha A dagger, e to the A right? Oh my God, there's a clock in there. Of course, it's telling me what the time is in Baltimore, but anyway, it's still okay.
It's 1 hour.
Okay. What is this? When this applies to the vacuum, well, now I could do what Matt suggested, write this out in a power series. But every time the annihilation operator is the vacuum, I get 0. So this is going to be e to the 0, which is 1. And now I'm going to write this out in a power series, alpha to the n, a dagger to the n, over n factorial. And what happens when I apply the annihilation operator to this? Well, I'm going to get the Fock state. Recall that n is right? That's how it's normalized. You remember that? And thus, this is equal to yay. this is equal to the coherent state. So I can apply the coherent state to this, and I'm sorry, I can apply this is a very useful relationship that algebraically that we'll use a lot. That I can think about the coherent state as a displaced vacuum, displaced in phase space. Okay? There's another algebraic relation I can get at here, which is the following. I ask you the following question. How would I look at the unitary transformation on the annihilation operator through the coherent state? How would I calculate that? Do you remember? Generally speaking, I'd ask you the following question. If I had e to the minus a b e to the a, how do I calculate that?
You just erase it.
Was that?
You just erase it. It wasn't your assignment.
Yeah, it was there, sort of. Right? That's also a form of Baker-Campbell-Hausdorff, chapter 1 of Saccharine. I'm sure you've seen it. How do I calculate that?
I know the first term is B.
What's that?
The first term is B.
Yeah, that's pretty good.
It's
It involves the multiple commutators, right? This involves the commutator of A with B n times over n factorial, right? Where this is A with A with A n times. When n is 0, it's just B. So, Stuart, you're right. The first term is B. And I challenge you to show easily that this is this. So, the phase space displacement operator displaces A by this. I'll give you another thing that's true if I looked at the unitary transformation of the position operator. Oops. Right? I'm displacing, P is the generator of displacements in position. It displaces the position operator. A unitary transformation does that in that way. So, with this said, another way of proving this is just to take A and apply it to the coherent state. That should be the same as this. Right? But now what? How do I bring these through? Well, I can do a commutator if I want, by just putting D on the other side, or stick in a D dagger D, or a DD dagger. Right? And what's this? Well, it's right there. So this is equal to D alpha A plus alpha on the vacuum, right? Because this is A plus alpha. That's what we just wrote, right? So D dagger AD is A plus alpha. So I stuck that in. A acting on this annihilates it. So this is equal to alpha so indeed, this is an eigenvector of A, the annihilation operator, with eigenvalue alpha. There are so many of these tricks of the trade, and we just got to get used to them. Okay? the displacement operator is a good one. You can use this all over the place. All right, we're kind of running low on time, but I want to talk about one other aspect of this. Let me come back to this. I'm listening.
I didn't understand the very last equality that you wrote.
This guy?
Yes.
So what I did is I applied the annihilation operator to the vacuum,
Uh-huh.
and this term went away.
Oh,
And then this is just a number,
put it away.
and I just put it on this side of the equation.
I see.
That's what I did.
Thank you.
Yep. Okay, cool. I want to look back at this picture over here in phase space of my coherent state. So the coherent state, as we said, was something that had minimal fluctuations in the quadrature. The classical complex amplitude has these two quadratures, x and p, right? But we can also think about it as having an amplitude and a phase, right? Any complex number has a real and imaginary part. They represent the quadratures of the oscillator. It also has an amplitude and a phase. The amplitude, of course, is equal to the square root of the mean of this squared. Okay. Now, from the quantum perspective, the thing that was the complex amplitude is like the annihilation operator, which has the Hermitian and anti-Hermitian parts as the quadratures. So now the question is, can I express this in terms of an amplitude and a phase? And what are the fluctuations, how it's the relationship of the number fluctuations to the phase fluctuations? We saw there's a relationship in the quadratures, that's the Heisenberg uncertainty principle. What about number and phase? Bless you. So, this would be given by what we would call the polar decomposition of a matrix. You guys know about the polar decomposition? It's not something that we often learn about, but we can always think about a matrix as being expressed in terms of the square root That's what's called the polar decomposition. There's a problem, as we will see. This is the square root of n. And we would say then we would have a number operator and a phase operator. But there's a problem. It's true we can write down the polar decomposition of a matrix. Always. We can always take a matrix and write down a polar decomposition in terms of a positive operator, an operator that has only non-negative eigenvalues, and a unitary operator. A unitary operator is the exponential e to the I times a Hermitian. So any matrix can be expressed as the product of a positive operator and a unitary operator. But this ain't no matrix, because I live in infinite dimensions, and sometimes infinity matters. And so let's see why. And there's some subtleties then about what we mean by the phase operator in quantum mechanics, and why there ain't no phase operator. So let's just quickly say that, and we'll finish this up next time. So, let me define A as the square root of n times an operator I'm going to call that. I'm going to put the big hat over that, where the square root of n operator is equal to this. That's a perfectly good operator. It's an operator whose eigenvectors are the Fock states, and whose eigenvalues are the square root of n. That's a fine operator. This operator, I'm going to define as this. This operator takes n to n minus 1. Now, is this a unitary operator? It kind of looks like one, but it's not quite. I'll just give you a little aside. If I have two bases, these are two bases for Hilbert space, then an operator that maps one basis vector to another is a unitary operator if these are orthonormal bases. This is one way to write down a unitary operator. You can check for yourself that u dagger u is 1. It takes the basis to its image. It rotates the basis. That's a unitary operator. You may not have seen that in that form, but that is. Now this looks kind of like that. But there's a problem, which is the n minus 1, right? If I look in particular at is this the identity? It's not, because it starts at 1. The problem was that this thing wasn't from minus infinity. This is the identity minus the projector on. So this is not a unitary operator. Therefore, there does not exist a phase operator. Makes things complicated, but we want to talk about the question of number phase uncertainty. It's kind of equivalent to the problem of the energy-time uncertainty principle. In a way, that's a complicated mathematical thing to write down. But nonetheless, there is some relationship, a trade-off, between a state that has a well-defined number and a well-defined phase. The Fock state had a perfectly well-defined number, but a completely uncertain phase. There's a trade-off. If we're going to have a state that has some notion, a wave packet that has some well-defined phase with some uncertainty, it has to have fluctuation in number. We can't have a state that has a well-defined number and a well-defined phase at the same time. It's a little bit complicated because we can't use our usual Heisenberg-Robinson uncertainty relations involving the commutators of Hermitian operators, because there ain't no Hermitian operator that defines phase. But nonetheless, it's a meaningful thing, and we'll finish this up next time. All right? To be continued. Have a good afternoon.